Hello everyone, my name is Jake Sekosky,
My name is Martin Heraldez.
and this is our lab report on semiconductor light sources. This is lab 10 of OPTI380. So essentially this entire lab is about comparing and contrasting the laser diode from the laser emitting diode. We're first going to start off by measuring things like cavity length and then work our way more towards the optical properties such as emission spectra, polarization, beam divergence, and then seeing how they both function under power.
So in part A, our goal is to examine the emission region and cavity structure of both a laser diode and an LED. We began by calibrating the image scale using a ruler to determine the conversion between pixels and millimeters. We captured images of the LED emitting at the 3 different lights and recorded the cavity length of the laser diode. So we were able to capture 3 distinct images of the LED emitting at 3 different colors by adjusting the drive current. On the bottom left, we measured the cavity length of the laser diode to be the black square, and on the bottom right, we have lasing at a very low drive current. We found our calibration factor to be 406 pixels per millimeter, which allowed us to convert our 266 pixel LED length to 0.429 millimeters squared of area, the laser cavity length to 0.739 millimeters, and the mode spacing to 5.8 gigahertz. In part B, our objective was to compare the spectral characteristics of the LED and the laser diode. We used the OSA to record the output spectrum of the laser diode as we gradually increase the drive current. We took measurements below threshold, at threshold, and above threshold before repeating with the LED.
Here are pictures of our emission spectra. However, upon further evaluation, we realized that this was not what was supposed to happen, as below the threshold was supposed to be more broad, and then as you increase the threshold, you would get more distinct peaks. We apologize for any errors that we made in the report, including this one where the mode spacing we calculated in this portion was 1.6 nanometers. The part A result should have been around 0.2 nanometers using the equation on screen. However, the part we did get right was that we saw a peak at around 630 nanometers, which is very representative of what we should see in a red Heine laser.
Part C, we measured the beam divergence and polarization characteristics of both the LED and laser diode. To begin, we mounted each device on a rotational stage and recorded the output intensity as a function of angle to determine beam divergence. Next, we introduced a polarizer into the setup and recorded the maximum and minimum transmittance of both the LED and laser. The LED had the widest emission spectrum, followed by the laser diode with its major axis parallel to the junction plane, and then the laser diode with its major axis perpendicular to the junction plane. The LED yielded a polarization ratio of 1, while the laser diode yielded one of 6.5. In part D, we measured the optical power of the LED and laser diode using an integrating sphere. The LED was connected through a power supply and multimeter, and its current was increased from 0 to 40 milliamps in 4 milliamp steps while recording power. The same procedure was repeated for the laser diode, with special attention to blocking straight light.
We see extreme differences between the laser diode and the LED when it comes to power. Both of them linearly increase when we turn up the current. However, the laser diode takes more time for a greater amount of power, while the LED takes less time for less power. In conclusion, the LD greatly differs from the LED, having a stronger polarization, more power, and a more narrow emission. We were also able to find mode spacing for the LED using theoretical calculations that lined up very well with our actual values.